Hey folks, welcome to the video. This is part 3 to simple harmonic motion. In parts 1 and 2, we found two types of solutions to the simple harmonic motion equation. This time we're going to relate those two. We're going to see that they're equivalent to each other, and we're going to do this using linear independence. Let's get to it. Last time we examined the simple harmonic motion equation. We found two solutions, one that's a cosine omega t plus b sine omega t, and a second that's a prime cosine omega t minus phi. The first one has two trigonometric terms, the second one has one trigonometric term, but with a phase phi. Today we're going to see that these two solutions are equivalent. In particular, we're going to ask the question, when are they equivalent? What values of a prime and phi will make these two solutions equivalent? To do that, we're going to use the concept of linear independence. So let's talk about that first. So linear independence, the way we can think about it is using a simple picture of the real plane, R2. R2, the real plane, is given by the span of two basis vectors, one in the x direction and one in the y direction. We can say that any vector a comma b in R2 can be written as a linear combination of these basis vectors, a times 1 comma 0 plus b times 0 comma 1. That's what it means for these two basis vectors to span the space R2. But why are they linearly independent? They're linearly independent because there is no constant c such that 0 comma 1 is equal to a times 1 comma 0 and vice versa. So we cannot scalar multiply one of these basis vectors to get the other. In general, linear independence for a set of vectors says that each vector in the set cannot be represented by a linear combination of the other vectors in the set. But that's a topic for another video. For our purposes today, in a space spanned by two basis vectors, we say that those two basis vectors are linearly independent if they are not scalar multiples of each other. Okay. So how does that relate to the solutions to the simple harmonic motion equation? We note that we can represent cosine of omega t and sine of omega t as vectors in their own right. They're vectors of function spaces. They are functions, but we note that cosine omega t cannot be written as a scalar multiple of sine omega t. So we can say that cosine omega t and sine omega t, the set of these two function vectors, is linearly independent. So what does that mean? We can draw a space where the x-axis corresponds to cosine omega t and the y-axis corresponds to sine omega t. And in this space, we have a vector sitting at a on the cosine omega t axis and at b on the sine omega t axis. This vector corresponds to a cosine omega t plus b sine omega t. And we can ask the question, what if we were to rotate this space by an angle phi? If we were to rotate this space by some angle phi, well then what we would have is a new space that would look something like this. And our initial vector would lie horizontal, would lie on the horizontal axis of this space. The question is, what are these two directions? The horizontal direction in the first picture, the left-hand picture, is cosine omega t. If we rotate that vector by an angle phi, then this corresponds to the function cosine omega t minus phi, where we've rotated our basis by an angle phi. And the vertical axis here corresponds to sine omega t minus phi. Now note that the length of our original vector a cosine omega t plus b sine omega t has remained the same. The length of a cosine omega t plus b sine omega t is, well, using Pythagoras' theorem, is a squared plus b squared, because this is the horizontal distance and this is the vertical distance. So that's the length. The length has remained the same. We've only rotated our basis. So the length of this vector here is still the square root of a squared plus b squared. But we can also write this vector as some a prime times this basis vector cosine omega t minus phi plus b prime sine omega t minus phi in this new basis. We note that because it has no component in the sine omega t minus phi direction, b prime is 0. So this vector is a prime cosine omega t minus phi, where the length of this vector is a prime. But we know that the length is also the square root of a squared plus b squared. Thus, a prime, the length, is a squared plus b squared. And the angle phi, we note that the tangent of phi is given by this vertical distance b over the horizontal distance a. So under these two conditions, a cosine omega t plus b sine omega t equals a prime cosine omega t minus phi. And so these two solutions are equivalent.
Well, I hope you all found that interesting. Some quick news. Today, I hit 200 views on this channel. Quick shout out to my 200 views Sanjana Ray and my cameraman Ashwat Suryanarayan. Thank you so much to everyone for watching. Like, subscribe. I'll see you all next time.